Okay, we talked about this already, so I won't spend too much time, but imports. Scope, along with applying to variables, also applies to functions. And sometimes if you've got a lot of functions, we don't want them all stored in the same file. We might want to organize them a nice way. For example, we might want to put all of the math functions in one file and all the, I don't know, all of the string-related functions in another file, and so on and so on. And that's how we break it down. In Python, you get a lot of functions for free. In fact, they're part of what they call the standard library, a bunch of functions and functionality that a programming language gives you for free to use because, I mean, there's a lot of like standard stuff people might want to do, like calculate the square root of something. It'd be kind of a pain to have to write that function on your own, so they give it to you for free because that's handy. And they call that the standard library. But because there's a lot of functions, and there's no sense in loading up all these functions if you're not going to use them, Python's very economical with what it loads up by default. By default, it gives you a minimal set of very often used functions like print, but it doesn't include everything automatically. Because so far, we haven't really used square root very often, but it's nice to have access to it when we need it. But Python's not going to load it up because that's just a waste of resources. So instead, if you want to make use of some of these functions, you need to go to your way and import it. So for example, the square root function, the sqrt, that function exists, but we can't use it unless we import it. And we import it by saying, well, import math, because it's stored in the math library. Now, to be very clear, no one would expect you to memorize what functions are in what library. No, that's ridiculous. No one would do that. Instead, you would just be like, you'd go to Google and say Python square root, and you'd see, oh, it's in the math library. Oh, okay, I'll import math. So like, don't worry about memorizing this stuff. No one would expect you to know this automatically. You know, after enough experience, you'll get a sense of what's where. But when in doubt, you just look up where it would be. If I don't import math, like let me show you. If I say sqrt of 4, print, no, let's do a equals print a. If I do that, it's going to say sqrt is not defined. So what I do is I say import, import math. But that's still not quite right. I've imported math, but I still can't use square root. Well, that's because math doesn't, the square root function isn't like here. It's in the math. It comes with math. So in order to use it, we would say math dot square root. And there we go. And in fact, you may have noticed something real quick. If I say math dot, you'll see like this giant drop-down list. And this is actually all the functions that are available in the math library that I could now use if I wanted to, which is kind of neat. So that's neat. This is a collab thing. We could even say import string, I can't remember. No. Maybe, yeah. String dot, yeah, and there's a bunch of functions in there. Yeah. The drop-down list is like a collab thing. And a lot of other IDEs have it built in too. But the fact that math is there and string is there, that is a Python thing. And in fact, you can go like, okay, math module is a very popular one. In fact, here are the actual Python documentation, like the actual documentation for math. Now, warning. Before you go use any function, it's probably a good idea to read what the documentation says. For example, okay, what's sqrt? So this is the official documentation from Python. Sqrt, no. Return the square root of x. Okay, well that one's pretty obvious. But you have to be careful because, for example, with like the trig functions, look at cos. Cosine, math.cosine, return the cosine of x radians. If I didn't read this and I assumed it works with degrees, this wouldn't work the way I want it to. I'd need to have radians in order to have this work properly. So it's always good to have a look at the actual documentation. Now, you may notice, too, if I were to say over here, math.cos, it'll actually, again, this is a Colab thing, but it'll actually tell you what's in the Python documentation. Return the cosine of x measured in radians. So this will actually kind of give you a glimpse of the actual documentation, which is nice. But the official documentation, you can find it on docs.python.org. And this is just the math thing. There's something called the standard library, which obviously don't go through this and read through it all. But there is a lot that you get for free. Memorizing this would be an absurd thing to do, and only crazy people would do that. But, you know, there it is. It's a reference. So if you ever need to use something, it's a reference. It's there for you, which is nice. Oops. Was I frozen or am I good? Good still. Now, comments. We've seen these already, but I haven't explicitly talked about them. Comments are lines or chunks of words in your code that Python ignores entirely. As far as Python's concerned, it's a blank line. Comments exist for humans, the programmers, to write details into their code, to maybe explain things a little bit better for somebody. In order to write a single line comment, you do like hashtag, and then you just write whatever you want. Now, ideally, you want your code to be as self-descriptive as possible, but sometimes, even if you wrote the code really nice and it's like self-describing, it's still a little ambiguous and unclear about what it's actually doing. For example, here's an example, right? You know, a lot of people in here might look at that and be like, well, that's the Euclidean distance between two things. Take the difference of the x's, square it. Take the difference of the y, square it. Take their sum and get the square root of it, or power of a half, whatever. Right? A lot of people might look at that and be like, okay, that's Euclidean distance. But a lot of people might look at that and say, what the hell's that? Like, I would argue that that code's pretty self-descriptive. Maybe if my variable was called like Euclidean distance, that would be better. But maybe let's just add a comment to this code. Calculate the Euclidean distance between 2 points. Oh, okay, yeah. So like you could be very explicit in describing what the hell's going on here. So comments are a great way to add details. It's always important to have very clear code. You want your code to be as clear as possible. But sometimes when you're worried about like if this code's really not that clear, add a comment and describe it. Now, sometimes students get really worried about having their code so detailed that they will have a comment for every single line of code. That's a terrible idea. That's a crazy idea. Don't do that. That's silly. No, you only comment the things that need comments. You can do comments above. This would be a silly comment to include because taking the square root of 4 is quite clearly taking the square root of 4. I don't need to describe that. I'm just showing you. You could do a comment on the line above sometimes, or you could even do, like on the same line, something like that. You know, that's entirely fine. You can do that. So comments, there you go. You can even do like block comments by doing, these are all commented out. Like as far as Python's concerned, those lines there aren't code. It just ignores it. It's just words. And then finally, docstrings. These are super important. Even if your code is very self-explanatory, even if a function's very self-explanatory, we should always write our docstrings. In fact, you must always write your docstrings. If you don't, you're going to get in trouble. A docstring is a special comment that you put in your function to describe what the function does. But not only do you describe what the function does, you describe what are the inputs and what are the outputs. Sometimes this feels rather silly because it is pretty straightforward, but often our functions get complex enough that they need sufficient description. And you'll see examples of this in the assignment 1. There are things that have docstrings in there already. So here's an example docstring. We use the 3 quotes, 1, 2, 3. And you'll notice that it starts immediately after the signature line. The signature line is like the def line. Quote, 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 convert a temperature from Celsius units to Fahrenheit units. This function has one parameter, so we include that in the detail. We have a colon, param, to signify it's a parameter. And then we say what it is, temp in Celsius, colon, the temperature in Celsius to be converted. Return the temperature in Fahrenheit. There. That is a docstring. That is a really good docstring. What's really nice about these docstrings too is, like, if you look at the Java docs for that math library, all of those descriptions of what each function does are actually their docstrings. That documentation that we saw on the website was actually generated from the docstrings. That's why the format of the docstrings are very important. That's why we put it right where it is. We use the colons, param, to signify it's a parameter, and the return and whatnot. In fact, this is so powerful that if you're following the instructions on how you're supposed to do it, watch what a common modern IDE will do. Oop. So if I call, what is it called? Celsius to Fahrenheit, look. It even comes up with a pop-up description that is literally the docstring. So these docstrings are standardized, there's a couple of different styles, this is the style we're using, but they're a standardized way of describing a function such that all of these other tools that are used to the standard can make use of those docstrings effectively, which is really nice. So from now on, anytime you write a function, you will write a docstring for that function. Any questions about any of that? All righty. All right, propositional logic. I'm going to teach you something that you already know. This isn't going to be crazy. If you struggle with this, you're thinking too hard. So sometimes there are statements, there are things that can be evaluated to what we would call a Boolean. Something that's true or false. It's one or the other. It's not in between. It's not a little of one or the other. It's either true or false. That's it. So, for example, this course focuses on introductory computer science. True. This topic is titled not logic. False, because it's titled propositional logic. It's rather intuitive because this is how you've been operating as a human since you were this big. So you are pretty familiar with these things. You're also familiar with some very important operators that we use on Booleans. So when I say operator, think of addition. You learned addition in, like, what, grade 1, if not before, right? It's that little plus sign. So the plus sign is an operator that takes two numbers and it gives you back a number. There's also another operator, subtraction, but it works differently. It takes two numbers and it gives you back another number, but it works differently. Multiplication, division, these are operators. They're like functions, but written a little differently. Well, we have more operators for Booleans, and, or, and not. But these operators will take two Boolean values and give you back another Boolean. And you are already all experts in Booleans and these operators because you use these on a daily basis, every day for decades. So this right here is a truth table. So right now we're going to talk about these Booleans and these operators very explicitly, and then I'm going to show you how, yes, in fact, you have been using these things. So right now I have a truth table. And what I've done is on the far left, I've got A and B. A and B are just two statements of fact that can be evaluated to true or false. And I'm only going to think about these things in terms of true and false. Okay? Now, a statement can be evaluated to true or false. If I were to say, am I wearing a shirt? True. Am I wearing shoes? Help me out here. Come on, wake up. Am I wearing a hat? Very good. Did anyone in here say no? Because if you did, leave. It's true and false. Not yes and no. It's true and false. Okay? So, am I wearing a hat? False. Okay, perfect. That's a statement, but it got evaluated to a Boolean, which is false. So imagine I have A and B. These are statements that are evaluated to true or false. What those statements are, I don't really care. They get evaluated to true and false. And what I've done on the far left, I've created every possible combination of these Boolean values. I have true, 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 false, false, true, false, false. There's 4 combinations of these 2 values. Okay? Cool? Yes? Happy? Sad? Now, if I were to say A and B, what do we notice? Well, A and B is an operator that gives me back true only when both A and B are true. Otherwise, it's false. Or, on the other hand, gives me back true unless both statements are false. And then finally, not A is just the inverse. So what's not true? Say false. False. Could say false, everybody. What's not true? False. What's not false? True. Look at that. You're a pro. So now if you're like the and or, no, let me put it like this. Am I wearing a shirt and shoes? True. Am I wearing a shirt and a hat? False. You're a pro, right? Am I wearing a hat and a watch? False. Right? Yeah, see, you know this. How about, am I wearing a shirt or shoes? True. Now this time it could actually be a little funny because English has some ambiguity when it comes to like exclusive or. Basically, if they're both true with an or, yeah, it's true. Sometimes people think, should it only be one or the other? That's a different or. That's called exclusive or. And there's some actual like funny thing with the English language that has ambiguity with this, but don't think about it too much. Am I wearing a shirt or a hat? Hey, wait a minute, yeah. Am I wearing a hat or pants? Am I wearing a hat or a watch? Right? See, you know this already. All we're doing is we're formalizing these ideas you are already experts in. It's weird to think about these things in terms of they're like atomic units, but that's what we're doing. That's a lot of what we do in computer science. So this is the truth table. Something that's true, something that's true. If we end it, we get true. If we or it, we get true. Something that's true, something that's false. If you end it, you get false because only one was true. True. And only gives you back true if both are true. Okay? Cool. So if I say true and false, what do you get? I know this one's tricky, but you're right, it's false. It's tricky because we're not used to thinking of the statements as to what they evaluate to. In our brains, we kind of skip that step. But really what we have to do is he wearing a hat? False. Is he wearing a shirt? True. False and true, that's false. That's really what your brain's doing, but you've skipped a bunch of steps because you're like, no, right? So it's important to slow down. Remember, if you've skipped those steps, you're being a bad computer scientist. Computer scientists are too stupid to make that jump. You have to think of it, each individual little step as you go. Any questions about this? This is called the truth table. It's a common way to demonstrate this type of stuff. Yes?
How does true and false equal false?
Because if you have a statement that's true, and a statement that's false. Let me put it this way. Am I wearing a hat?
No. False.
Let's try again. Am I wearing a hat?
False.
Am I wearing a shirt?
True.
Am I wearing a hat and a shirt?
True.
You're thinking too hard. No, I'm not wearing a hat and a shirt. I'm only wearing a shirt. I'm not wearing a hat. So let's try it again. You know what? I'll flip it. Am I wearing a shirt?
True.
Am I wearing a hat?
False.
Am I wearing a shirt and a hat?
False.
That's why. Right? It's hard to explain why, where it's just like, because it is. Right? Am I wearing, let's try again. I need another volunteer. I reserve the right to make fun of you.
That's fine. There's not much left.
Am I wearing a shirt?
True.
Am I wearing a hat?
False.
Am I wearing a shirt or a hat? Don't think about it too hard, just answer the question. True, right? Because I'm wearing one of them. I'm wearing a shirt or a hat. You're wearing a shirt, so yeah, it's fine. Now, an interesting thing is, let me ask you, okay, everyone, slow down, and I'm going to ask a question. I want you to actually think about, don't jump this one. Think slowly and cautiously, because I'm going to prove to you that you're a goddamn genius right now. Okay? Am I wearing a shirt, or don't answer out loud, just think. Am I wearing a shirt, or do I even need to ask the second question for you to know the answer? No. I have something that's true, or I don't give a shit. If one of the two is true, the answer's true. And we can flip it. Am I wearing a hat, and it doesn't matter. No matter what, because I'm not wearing a hat, the whole statement must be false. So it's kind of neat. Anyways, any other questions about this? If you're struggling with it, you're normal, but you're also thinking too hard. How does the not A work? Am I wearing, who asked that? Am I wearing a hat? Am I not wearing a hat? Yeah, that's it. There you go. That's how it works. You just take the result and flip it. That's it. So am I wearing a shirt? Am I not wearing a shirt? That's it. That's all there is to it. So the not, and here's another important thing too. The and and the or are binary operators. They're operators that has two operands, right? Not is a unary operator. It only uses one. So not true, that's false. Not false, that's true. You just flip it. That's all it is. In more general mathematical speak, not is the inverse, like it inverses whatever it is. Other questions about this? One thing I want to emphasize here is, it's funny, every year, like on the final exam, I will ask questions about true or false. And if I were to ask a question like, am I wearing a hat and a shirt, you'd be able to answer it. But if I put a question like this on the exam, I don't know if this works. Nope. So if I ask you a question with a statement that can be evaluated to true and false, and then use like ands and ors, you're fine. But when I ask a question like this, what's the result of this? So many people get this wrong. You're wrong. Because for some reason, in spite of me yelling at them all semester about slowing down and thinking about evaluating each statement and then taking the result of each statement and using the binary operators, like, am I wearing a hat and am I wearing a shirt? You go, well, no, that's false because he's not wearing both, right? Yeah. But really what you're doing, am I wearing a hat? False. Am I wearing a shirt? True. False and true, or reverse, true and false, well, whenever you have something, and it only gives you back true if both are true. So weirdly, people get this wrong, and it's because they're trying too hard. They're skipping steps. Be a dumber programmer. That's really what I'm trying to say. So, is the sky blue and is the water wet? True. Is the sky blue and is it over 100 degrees Celsius outside? False. It's sure the sky's blue, but it's not also over 100 degrees Celsius outside. Maybe it was yesterday. Is the sky blue or is it over 100 degrees Celsius outside? Well, that's true because, I mean, the sky is blue. I don't give a shit about the other question. Is it not over 100 degrees Celsius outside? True, because it's not. And is the sky blue and is it not over 100 degrees Celsius outside? True. See how they all kind of work together? In fact, that last one, we're using compound statements where we're adding additional operators. But we could all intuitively figure it out because, you know, we operate at that level. Questions, thoughts, concerns, comments, anything? Ask now before we move on. All right. So you may have noticed for and, both statements must be true to produce true, otherwise it's false. For or, only one must be true to produce true, otherwise it's false. And not changes true to false and false to true. That's the summary of what it is. Cool. So for or, both statements being true produces true. And there's another operator called exclusive or that's true only when one of the statements is true. Exclusive or is not to come up. We're not going to talk about exclusive or really, but it does exist and it can be handy in some situations. I'm just bringing this up here to eliminate ambiguity because or in the English language can be a little ambiguous about is it exclusive or not. And if you were scratching your head about what the hell I was just saying, it doesn't matter. Ignore it. All right. Okay, a Boolean type. Well, Booleans are a type in Python and in a lot of programming languages, like integers and strings and floats, but it's its own type, Boolean. In fact, we can prove this. Prove or at least demonstrate. Yeah, crash. First of all, I say print true, and you're like, well, it just prints out true, but it's not the string true. How do I know it's not the string true? Who can tell me? No quotes. I mean, I could add quotes. Well, now it is the string true, but now it's the value true. Okay? Warning. It's not true. If I do this, it's going to be like, what the hell is true? It must be uppercase. Note, Python's actually the weird one. In many other programming languages, Booleans start with lower cases. I don't know. It's a whole thing. But in Python, uppercase, true. And if you don't believe me that it's its own type of true, we see bool for Boolean. Cool. We also have false. Whoops. False, it's a Boolean. Booleans are a type, but they can only take on one of two values. Alternatively, integers, they're a type, but they could take on a hell of a lot more values. 1, 2, -7, 44, whatever. They have a lot of different values. Booleans are a type, but they can only ever be true or false. Those are the values that they can take on. Cool? Happy? Sad? Yeah, okay. Unlike integers, strings, floats, they can only take on one of two values, right? And then Boolean operators. Well, we just looked at some. Boolean operators, just like arithmetic operators used on integers, Booleans have and, or, and not. I already showed you this. Consider the plus sign. Well, with integers, that's an operator that does addition. With strings, what does the operator do? Concatenates. So Booleans, it's the same idea, but you use it on the Boolean operator, same idea, but you use it on Booleans. What should I see? Whoop. When I hit run, what should I see? False. Who said false? Get out of here. Who said it? Be honest. It was you this time? Everyone laugh at him. See? Now, what about this? Here, I'm gonna save you. I'm gonna put you on the spot. What should this say? Hey, you've redeemed yourself. There you go, right? What about this? Ooh. What is this going to do? Why? Well, true and not false. What's not false? So true and true is? Hey. What about this? Well, it's true. Because true and false is false, and what's not false? True. In fact, I could write whatever the hell I want over here. And I know that this is going to, well, this will crash, but presumably if it's a valid Boolean expression, because I know that the thing on the left-hand side of that or is true. I have true or, I don't care what. True or whatever is always true. Thank you. Now, those are Boolean operators, but we have other operators now. Now we're getting a little wild, but trust me, you're probably going to be okay with this. We have comparison operators. A comparison operator, we can use them with other things, but let's talk numbers for a second. A comparison operator is an operator, like addition, like the Boolean operators and, or, and whatnot. Comparison operators are often Boolean, binary operators. They take two inputs, two operands. The comparison operators, in the examples we're going to see, takes two numbers and gives me back not a number, a Boolean. Now, if you're like, whoa, you've been doing this since like grade 1. Who here remembers learning about less than and greater than? Right? When I learned about it, we did it in terms of like Pac-Man, right? And Pac-Man wanted to eat the bigger thing. Other people are like, we did alligators. The alligator wanted to eat the bigger thing. Okay, fine. Whatever you want. But comparison operators, you know what these are. I'm going to ask you a question. Print. Is 6 greater than 5? Well, clear this out because that's not relevant. Is that a true or false statement? It's a true statement. Whoa, look at that. What about this now? It's still true. Well, let's break it down. Everybody, is 6 greater than 5? Is 5 greater than 6? I have a true statement or a false statement. What do I get? Because true or whatever is true. In fact, this could be a giant expression on the right-hand side. I know it's like one operator, but imagine this goes on forever and it's a huge calculation. We know the result is true because the left side of that or is true, and true or anything is true. Does the computer even need to actually evaluate the other side of the expression?
When it comes to this, is the order of operations, like how does that work? Is there anything to take note of?
So, very good question. Let's see if we can find Python. I want to find the, wow, this isn't, here we go. Expressions, here we go. Okay, this is a big web page. Here we go. There is an order of operations. Now I'm going to warn you, this table includes a hell of a lot more operators than you're used to seeing. It includes a lot more operators than I'm used to seeing, because some of these are fairly esoteric, you don't use very often. But there does exist an order of operations. Remember learning in math, like BEDMAs, remember? You know, brackets, then exponents, and then your multiplication. It's the same idea, just more, right? And based on what I've already told you, what operator do you think is at the very bottom of this list? The one that has the least biggest priority? Ignore the fact that it's got eyes, but the equals, the assignment. Assignment is always the last thing that happens. But then the Boolean operators are some of the last things that happens. Then we have our, where are the comparison operators? It's not even sure. The comparison operators have a higher priority than the Boolean operator. So there is an order of operations. Now, you might be thinking to yourself, I have to memorize this. I mean, you can if you want, but I didn't. You want to know what I do? When in doubt, just make it as goddamn clear as you can by doing something like this. Like, what's the order of operations? I don't care. Let's just make it clear. Now, there's no ambiguity. We'll do the brackets first. I'm happy. That's what I do. So very good question, and just do what I do. Ignore it and just do brackets. So there is an order of operations, and it is well defined, but yeah. Although it's funny, actually, there is ambiguity even within our regular mathematical order of operations where you can get different answers even though you're following the order of operations, because there is ambiguity, but never mind. So, anyways, these are now comparison operators. They are an operator that will take two values and give you back a Boolean. All right? We're using numbers because they're easy to wrap our head around. So, is 5 greater than 3? Don't cheat. Is 5 greater than 3? True. Perfect. You're an expert. Is 1 greater than 7? You had to think about that one, eh? So here are the common comparison operators. Remember how I said equals doesn't mean equals? It means assignment. Because equals equals means equals. And it's a statement of fact. So if I say, does 5 equal 5? Well, that's true. It's a statement of fact. 6 equals 5. Well, that's bullshit. It's false. We all know that's nonsense. What about this? Is 4 less than 5? Yeah. What about this one? Is 5 less than 5? Come on, is 5 less than 5? False. Really? Yeah, it's false. Because 5 is not less than 5. If you're like, I don't know, that's kind of like an edge case. You're normal. This is an edge case. The answer of is 5 less than 5, I guess it does make sense, but it is an edge case of like, is it? If you're like, well, I don't know, there. That's less than or equal to, right? Is 5 less than or equal to 5? Well, it's equal to 5, so it's true. At this stage, you might be saying, I mean, these are silly statements. Is 5 equal to 5? No shit. Of course it is. Well, remember that right now I'm just playing with literal values. Imagine something like this. Right? There. Now, hopefully, it's a little bit more clear why I would care. Right? If I put in 7, well, it's false. Oops. If I put in 3, it's true. Right? Cool. So comparison operators take two different values and gives you back a Boolean. Does that make sense? Of course it does, right? And every reasonable person.
I mean, if it's done by Python, it has to be right.
You put way too much trust in Python. Anyone want to know why that worked?
Because it's binary where true holds the value 1, false is 0.
Exactly. Actually, technically, anything not 0 is true, technically, but it really depends on the environment you're dealing with. traditionally speaking, well, at least for Python, true and false are separate things. But traditionally speaking, if you go back decades ago, when we didn't have fancy languages like Python, the way you'd have false is 0. The way you would have true is 1. So by convention, true has the value 1, and 0 or false is 0. So that's why I could do something like this. Doesn't mean you should. I was just showing you because it's kind of a funny little quirk. What's this? 1, of course. 0 plus 1 is 1. Plus true times true. I want to be clear. You're probably never going to write this unless you're showing people how weird this is. Square root of true. Everyone knows that the square root of true is 1, right? I mean, it's the float one, though. Anyways, it's looking at me. So there's a bunch. We have equals. We have not equals. That's exclamation point equals. Alternatively, if you hate not equals, if for whatever reason on your way home you get hit in the head really hard and you lose the information of how the hell do I do not equals? I can't remember, you forget the fact that it's exclamation point equals. Don't worry, here's the hack that you won't forget if you get hit in the head with a baseball. True. So what's this going to tell me? False, because they're not the same, right? What's this going to tell me? Well, true, because true is in fact not false. But if you forget the fact that this exists, don't worry, you could just do this. It's exactly the same thing, right? Not equal is the same thing as equal, not. So for the sake of time, I won't do this one. But yeah, mind the use of 2 equal signs when checking equality. Remember, a single equal is assignment. Some variable equals 5 takes the value 5 and puts it in the variable some variable. Some variable equals 5 is an operator. That is a Boolean operator, a comparison operator. Checks if the value stored in some equal is equal to the value 5. In some older programming languages, this could become a bit of an issue if you accidentally mix these up. And for that reason, people do something called like Yoda-style programming, where you always put the literal on the left-hand side, so you can never accidentally assign something when you're trying to do a comparison. Yeah. Here's what I mean. If I had some, like, my super, right? And I want to check if my super important value is equal to 6, right? And I hit, here, oops. Right? And I want to check if it's equal 6. Okay, false. Great. Okay, great. But then, I don't know, my kid shows up and as they're screwing around and they go like this. And then, we're doomed. Right? We're doomed. This could never happen if you do Yoda style, which is, instead of saying my super important value never change me world dies is equivalent to 6, we would say 6 is equivalent to that. So yeah, that'll work. But if my kid comes along and does this, it's going to say I can't reassign the value of a literal. So it's a way to hedge against problems. Some people like this, some people don't. If you want to do this, great. If you're like, I hate it, it doesn't matter. But it could save you and the world, apparently. Composing operators, well, there is an order of operations, but if I were to say 17 plus 2 is less than 18, or 17 is not equal to 18, what's the result? True. Why? Well, 17 is not equal to 18, which is true, and I've ORed something, so I could be lazy and skip the other side. But if we want to evaluate it all, we could. 17 plus 2 is 19. Is 19 less than 18? False. All right. Is 19 less than, oh, this is me running it out the whole way. Perfect. There. We evaluated it. There is an order of operations. You could just evaluate it one step at a time. Does 101 equal 100 and 66 minus 17 less than 54? Well, if we calculate all this out, we go down, we can evaluate it to false. But like I said, once we know 101 equaling 100 is false, we're kind of done. I know that the whole thing must be false because false and I don't give a shit is false. That's just me saying that. Is 14 greater than 0 or is 6 not equal to 7 and 14 plus 17 less than 20? Well, is 14 greater than 0? True. Who's, what? True. Or, and look, we can evaluate all this, and we do. But again, once I know this is true, true or whatever is always true. Anyways. If you ever find yourself, though, now, everything I've shown you here, these are contrived examples of me showing you what you could do. In practice, if you end up writing Boolean expressions that look like this, you're probably doing something wrong. Okay? Sure, it'll work, and you might be technically correct, but you've got bad code. All right? Your code shouldn't look that crazy and hairy. So yeah, if you find yourself writing long, complex Boolean expressions, chances are you're doing something wrong. Even if you have long lists of conditions, you need to check in your program. There's a way to make it more manageable and easier to follow. Like you could break this down into multiple expressions, evaluate each, and just make your code a lot cleaner. Testing your code and type ins. Now, for those of you in lab yesterday, you got a sneak peek. And we won't have time to finish the topic today, obviously, so for those of you in lab today, you'll also get kind of a sneak peek. Writing code, I don't give a shit if you write code. I want your code to be correct. I want you to write correct code. And if you're writing a function, and you're like, here, I'm done, whose job is it to tell me if that code is right or not? Yours. I don't want to look at it. Prove it's right. Or at least do something useful to demonstrate that it is probably correct. We always write tests for our code. And here's the thing. If I don't even need to write the code, if I say, write a function to do X, Y, Z, and you're like, okay, write a function to convert Celsius to Fahrenheit. Do you need to write that function in order to know how it should act? Like, what would be correct? I know that, this is just because I know that even before writing the function, I know that if I ask, what's the Fahrenheit value of 0 degrees Celsius? Well, that's 32. Negative 40 is negative 40. I know that. I don't need to actually write the function in order to know how it should behave. If you say, well, no, I won't really know, well, then you don't know what the hell, then why are you writing a function if you don't know how it should behave? So we can even know how our function should act before we write our functions. It's always important to write tests for our code. And we're going to be doing that. We're going to do it with simple assert tests. Assert is a keyword in Python that is assert something, and if that something is not true, the program crashes. That's what we're going to do. Every programmer who's worth anything, any programmer that has a job, is writing tests for their code. They will not be, usually what happens is, if I'm a big software company, I've got this giant chunk of code that I'm selling to people or something. I work at Amazon and it's Amazon stuff. And I'm a programmer and I'm like, oh, I'm going to add this new feature, right? And I code it up. And I want to add my new feature into the big project. My boss is going to be like, where are the tests? And if I say, well, I don't have the test, they're going to be like, so do I fire you now or like at the end of the day? Are you seriously dumb enough not to test your code? What are you doing? Like, you always write your tests. The tests we're going to write are simple assert tests. And these are, by all means, sufficient for what we're doing. But as we go and our code gets more complex, these will be very limiting, and we will learn a new way to test it with a little bit more power. But these are sufficient and powerful enough to demonstrate correctness. And we'll pick up here on Tuesday.